Hi, everybody. Today we're going to do a topic called related rates. This is section 2.11. So let's look at this problem, and I'll explain what I mean by related rates. A pebble is thrown into a calm pool of water, causing ripples in the form of concentric circles, as you can see in this photo. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the rate? At what rate is the total area A of the disturbed water changing? So this is what we mean by related rates. In other words, they're giving us the rate of the radius. They're giving us the rate that the radius is increasing. They don't give us the radius of the air. They don't give us the rate at which the area is increasing or changing, I should say, but that area is related to the radius because we know the area of a circle is pi r squared. So there's a relationship between the area and the radius. So they want us to find the area. They don't tell us what it is, but they do tell us what the radius is, what the rate of the radius is, and we're going to use some clever calculus to figure out how to solve this problem. And if you think it's a coincidence that we're doing this topic after we did implicit differentiation and chain rule, well, maybe it's not such a coincidence. But let's just take a look. So I'm going to switch cameras now. I'm going to go and I'm going to solve this problem. Okay, here we go. So we have here, so the pebble is, let's see, let's just draw the picture here. The pebble is, so here's the circle. And here's the radius. And they're telling us that the RDT, there's the change, the change of change in the radius with respect to time, dRdt equals 1. That's a given. We want to find the ADT, the change of area with respect to time. That's what we want to find. And we want to find specifically what is it when the radius is 4. And that's all the numbers. Now let's see how this works. So the RDT, the rate of change for the radius is 1 foot per second. The radius is 4 feet right now. How is the area changing? Well, it's a related rate. Now, as we said before, it's related rate because the area is, again, we want to know the rate that the area is changing, and they don't give us that. They only give us the rate that the radius is changing, but the area and the radius are related. And what we want to do, being mathematicians, we want to find a mathematical equation that specifically relates the area and the radius. And that is actually a very famous equation. I'm sure you've all seen this before. Area is equal to pi r squared. That the area of a circle is equal to pi r squared. Now, don't get confused. A lot of people say, hey, pi's are round, they're not square. But that's not what this is saying. The area of a circle is pi times the square of the radius. Anyway, what I'm going to do now is I'm going to differentiate both sides with respect to time. Now, we're viewing the radius as a function of time because every second, every instant, as time changes, the radius increases. As time goes on, the radius increases. So we're viewing the radius as a function of time. Remember that. Radius is a function of time. So we're going to take the derivative of both sides, not d dx like normal, but d dt. So we have the a dt, again, I'm distributing on both sides, everything on both sides. The a dt is equal to, now the derivative of pi r squared is 2 pi r times the inner derivative, which is dr dt. Remember, because the radius is a function of time. So this is the outer part. Again, I'm just kind of labeling it for you. This is the outer part, and that's the inner part. Because r is a function of time. Well, dr dt is given to me. It equals 1. We want the radius. The radius is constantly changing, but we're looking to see at the moment when the radius is 4. So I'm just going to plug in 4 over here and 1 over there and just crunch it out. So dA dt equals 2 pi times 4 times 1. Because 4 is what was given to us, and 1 was what was given to us. And that's just equal to 8 pi. Of course, I wrote 8 pi, but we really mean, we really mean 8 pi, we really mean 8 pi square feet per second. So that's what we really mean. 8 pi, I'm going to write it this way, foot squared per second. And that, my friend, is the story, and that's the calculus. So by using calculus, and we're basically using implicit differentiation, chain rule, all this kind of cool stuff. And what we're doing here is we're taking two things that are related, and importantly, we're finding an equation that relates those two things. In this case, this is the equation that relates them right there. That's the equation that relates these two things, and we're finding that, and we're using that to get our answer. Usually in these problems, in these related rate problems, they give you every piece of information you need except for one thing, and that's the one thing you have to find. So usually in my experience, when you do these kind of problems, these related rate problems, they give you the DRDT, they give you the R, they give you all the stuff you need. You just got to figure out the proper equation. Once you get that equation, again, it's an equation that relates these two things. And this, we're talking about radius, we're talking about area. So that's an equation that relates radius and area. Once you get the equation and you differentiate it, you're going to see that every unknown was given to us. And then we crunch it all out, we get that final last unknown. And that is this question. We're not done with the video. We're just done with this question. So as a rule for these kind of problems, generally speaking, so we want to figure out the quantities that are changing, like we did in our previous problem. The radius was changing, the area was changing. We want to give them variables. R was radius, A was area. Then you want to find an equation that relates those quantities, and you're going to have to do that from your store. You have to do it from your store of mathematical knowledge. So here I happen to know that that formula A equals pi r squared. That's a pretty famous formula. So, and differentiate both sides of the equation with respect to time, because this is rate. We're talking about time now, and then plug in all the values that were given to us, and then solve for the thing that we want. And usually they're going to, like I say, it's going to be usually it's going to be easy as pi. I don't mean the number pi. I mean it's just an expression, easy as pi. Let's do another problem. All right, here's a nice one from the world of business. A company has determined the demand curve for their product is Q equals square root of 5,000 minus P squared, where P is the price in dollars and Q is the quantity in millions. If weather conditions are driving the price up $2 a week, find the rate at which the demand is changing when the price is $40. And just wanted to point out that the quantities here are Q and P, And these are the things that are changing because the price is changing, and the quantity is changing. They're both changing as time goes on, so they're both functions of time. And we have this nice equation. They actually now in this equation you're going to say, oh wow, where am I going to figure out to find an equation that relates these two guys? Well, they gave us the equation that relates them. So all we got to do now is just work the equation and work it out. So I'm going to switch cameras now, and I'll work it out now together. So summarizing the information they gave us, Q is equal to the square root of 5,000 minus P squared, which by the way is, as an exponent, is 5,000 minus P squared to the 1/2 power. You know, with calculus, it's always easier to write things with exponents. And they also told us that dp dt is equal to 2 when P equals 40. And we want to find dq dt. So we're going to take the derivative of each side. So dq dt is going to equal 1/2 5,000 minus P squared to the negative 1/2 power times the inner derivative, which is negative 2P. And times, I guess if you will, the inner derivative, which is dp dt. So this is kind of a triple chain rule because the outer function is the yeah, there's a lot of cool stuff in it. The outer function is the radical, the inner function is the P squared, and then the inner function is the fact that P is a function of time, P of t. So the derivative of that is just dp dt. Now it's really super simple wimple because we know that we know that this guy is 2, we know that P is 40, and now it's just a question of plugging in. So that's all we're gonna do is just plug in all the variables, and that's going to be, let's plug it in, 1/2 5,000 minus 40 squared, which is 1600 times negative 80 times 2, which is equal to, but notice that this is going to be a negative number, and it's going to, and if you crunch it all out, it's going to be roughly negative 1.37. So dq dt is going to be roughly negative 1.37, which means that the quantity is going to decrease when the price increases at 40. So the where do we go here? So demand is falling by 1.37 million per week when the price is right. No, when the price is 40. They always say when the price is right. That was an old TV show, I guess. Anyway, that is this lovely problem. It's been loads of fun, and we'll see you guys next time. Bye.